In question 5a, we have a piece of conducting putty in a cylinder 6.0 times 10 to the minus 2 meters long, with a radius of 1.2 times 10 to the minus 2 meters, and a resistivity of 4.0 times 10 to the minus 3 ohm meters. In part 1, we need to calculate the resistance between the ends of the cylinder. Well, for this we can use resistivity is equal to resistance times area over length, rearranging for resistance, putting in the values given for the resistivity, the length, the area is pi times the radius squared, gives a resistance of 0.53 ohms. In part 2, the cylinder is reshaped to have half the radius and 4 times the length. We need to find how many times greater the resistance will be. Well, halving the radius reduces the area by a factor of 4, so we'll increase the resistance by a factor of 4 in itself. Increasing the length 4 times will also increase the resistance by a factor of 4. Putting these together increases the resistance by a factor of 4 times 4, which is 16 times greater. In B, we have the original cylinder of conducting putty, and we need to describe how we could use a voltmeter, an ammeter and any other lab equipment to find a value for the resistivity of the putty. We need to include a labelled circuit diagram, which is here. So I have a power supply, which I can vary using this variable resistor. I have an ammeter in series with the putty, and a voltmeter in parallel with the putty. We also need to state what measurements we would take, account for how we'd use the measurements to determine the result, and how we could improve the precision of the measurements. Well, we place the cylinder in the circuit as shown, and find the current at a potential difference of, say, 1 volt. We'd then adjust the variable resistor to give potential differences up to 6 volts in 1 volt stages. The actual values I've given here aren't particularly important, but it's wise to give some values of the measurements you would take. We'd record the current at each value, and repeat these readings to find a mean. We'd plot a graph of current against potential difference, and the reciprocal of the gradient gives us the resistance. Then we'd measure the length of the cylinder using a ruler, the diameter using vernier calipers, and for both we'd take measurements in several places to find the mean. We'd calculate the cross-sectional area of the cylinder using area is pi d squared over 4, and we'd calculate the resistivity using resistivity is equal to resistance times area over length. We could improve the precision by measuring the diameter with a micrometer instead of vernier calipers,